Hi, everyone. My name is Keri McKiernan, and I'm a graduate student at Stanford University. Today, I'm going to be talking about an application I've been working on that uses Forest. On that note, the name of my talk is Estimating Gradients Using Quantum Computation in Forest. Okay. So why are gradients important? Well, gradients are absolutely fundamental to a variety of science, research, and engineering applications. I have two examples given here. First, the class of optimization problems. Gradients are absolutely fundamental here. Suppose you'd like to train a data model. Chances are you're going to be doing a gradient-based minimization of some loss function in order to build an optimized model. Secondly, suppose you're trying to simulate a dynamical system. What you're probably going to be doing is taking gradients of some interaction function, which will tell you how to propagate your system in time. So gradients are important. Now, how do you compute gradients? Typically, what's done is a scheme referred to as finite difference. And how finite difference works is you want to sample your function at the point of interest, depicted here at the origin, and you also want to sample your function some perturbation h from the point of evaluation. And what you're able to do when this perturbation is small, when h is small, you can do a first order Taylor expansion of your function. So when h is small, you can represent your function in this way. This is convenient because you can rearrange this expression to find an estimate of the gradient at the origin. Now, the classical scaling for this process is actually d plus 1. So it's dependent on the number of dimensions of your input domain. Now, quite amazingly, the quantum equivalent of finite difference actually just takes one query, which matches the scaling of the classic analytic version, if you're lucky enough to have an analytic derivative. Now, if you want to compute higher order derivatives, you're going to iterate these protocols, and you see that the quantum numerical version actually surpasses the classical analytic scaling. So in almost any case, the quantum equivalent is going to match or be faster than any classical approach. And this is particularly important for large number of dimensions. So if you want to train large dimensional neural network, or you want to simulate a large dynamical system, it's extremely expensive classically, but the quantum equivalent has the potential to be much, much faster. Okay, so the quantum equivalent of finite difference was originally devised by Stephen Jordan, and the problem is as follows. You have some function f, it's smooth, and it transforms from r to the d to r. And what you'd like to estimate is the gradient of your function f. Here we're going to be estimating the gradient as an n-bit binary fraction, represented here. This is the circuit for this algorithm, and we're going to break this down piece by piece. There are three main parts to this algorithm. You're going to initialize the system, then you're going to do a phase kickback, then you're going to measure the system. We're going to break down each of these programs. So first, initializing the system. This is this component of the circuit. First, so we have two sets of registers. We have input registers and ancilla registers. And what the ancilla registers are doing they're just doing work in the algorithm. They're not actually ever measured. So here we're preparing the ancilla registers. What we're going to do is apply an X gate and then take the quantum Fourier transform after we apply the X gate. And what that does is it prepares this register to a plane wave state. And this plane wave state is very important for the next step of the program. You'll see why. So the code to do this is actually very straightforward. All you have to do in PyQuil is import the X gate. From Grove, you import the QFT subroutine. And then from pyquil.quil, you just import pyquil.quil so you can build the program. And then you just have to use a little bit of Python to push your ancilla qubits through the X gate, through the QFT, and then build your program. So this might look kind of complicated, but it's more or less 3 lines of Python. Okay, we've prepared our ancilla register. Let's prepare our input registers. We see here that we need to apply a Hadamard gate to each of these input registers. And this is as simple as importing the H gate from pyquil.gates. And then again, with a little bit of Python, mapping our input qubits through this Hadamard gate and constructing our program. Okay, so in order to initialize our system, we need about 6-7 lines of Python, which is pretty good. So we've initialized our system. Now we want to do what's called a phase kickback. And this is a version of a phase estimation algorithm, and it's reliant on a black box oracle. Now, what the black box oracle is it's a unitary operator for which this particular eigenvalue relationship is held. So what that means is U acts on our ancilla register, and this was the reason we prepared our plane wave state. We want this particular eigenvalue. Now we apply this gate in a controlled fashion, and what that means is it essentially so-called kicks back this eigenvalue to the one component of the control register. So although this operator is acting on this register, since it's in a controlled fashion, it will push back the eigenvalue to the input register. So we know of a gate that will implement this on a plane wave state, and that's the phase gate. Okay, so you may be wondering now, what is f of x, and what does that have to do with gradients? Well, okay, first this is how we implement U. We're going to implement a controlled version, so we import this function for creating a controlled gate, and then we loop over each of our input qubits. Here's U. And then we build U, and we see that we're applying it to our ancilla qubit, but it's conditioned on what we're iterating over our input qubits. Okay, so what is f of x? Now, if you recall, we can do a first-order Taylor expansion of any function when h is small. Now, this is convenient when we implement this approximation in the argument of a complex exponential. For one, we can take advantage of translational symmetry of this function and ignore the global phase. And then if we look over here in the red boxes, f of x, we can utilize the substitution in equation 5 to go from f of x to h gradient of f at 0. So we now have a approximation for our gradient in the phase of this eigenphase. Okay, so this is the output of the black box. The output of the black box is then fed into the inverse Fourier transform, and that has the effect of pulling out the fractional component of the phase here, so that we're then in a convenient basis. Now we're going to do one more substitution. So our gradient is estimated by this binary fraction. Here, we're just working through some convenient properties of binary fractions and, again, exponential functions. And then we reach the substitution in equation 8. And if we look at our red boxes again, we're going to apply this substitution. And we see that the output of this circuit so far is going to give us something in the base of each of the components of the gradient estimate. Okay, so in order to apply this part of the circuit, all we have to do is import the inverse QFT module from qft.fourier, and then we just feed in our input qubits. So it may seem a bit complicated, but again, it's just a few lines of Python. Okay, so that's the phase kickback, and now we're going to do the last part of the circuit, and we're going to measure. So when we do that, we then just read out each of the components of our basis, and we can piece this together in order to get an estimate of the gradient. And then to do a measurement, we connect to the quantum virtual machine, and then we feed in our program, and we say we want to measure our input qubits. So then 3 lines, including the import. Okay, so in order to do all this, there's a wrapper that I've written, a wrapper function gradient estimator. What that looks like, it implements the functions we saw previously. where we initialize the system, we do the phase kickback, then we combine it. After that program's built, we run and measure it. So we measure input qubits. Okay, now I have a quick demo. Okay, so we're going to do a very simple simulation of a particle in a absolute value potential. So first we do some imports. This is going to be used to integrate our differential equation, import numpy. This is the wrapper function, just referenced. These functions are all helper functions just for converting between real decimals and binary fractions, and then some plotting imports. So we're not fortunate enough to have a real oracle to give us FFAT perturbation H, because that would be, for example, the output of something like an electronic structure calculation. Here we're just going to look at an analytic potential. And it looks like this. So it's the absolute value between 0 and 1, centered at 0.5, and then there are hard repulsive walls at 0 and 1. So we're going to start a particle over here and watch it. Well, we're going to do a simulation, gradient-based simulation of it diffusing in this potential. So we have, okay, so here's the setup. So we prepare our input registers. Then we use this wrapper function to build the gradient program, connect to the QVM, run and measure, and then we do lots of measurements so that we get good statistics, and then these functions are just for summarizing our statistics. Okay, so what this integrator does is it just updates iteratively the position, the velocity of the particle. And where the gradient estimation comes in is in the calculation of the acceleration. So force is the negative gradient of the potential. Force is also mass times acceleration, so we can arrange this to get an expression of the acceleration in terms of the gradient of the potential. So here, I actually I was doing a pure implementation with the quantum gradient estimator, and it actually blew up. So this is it zoomed out. This is it with a modulated domain. So you can see that it starts out fine. This is what we would expect. And then about the point where it hits the inflection, so this is the potential. So it's sort of not smooth at 0.5. So right when it gets near 0.5, it kind of blows up. And part of the issue with this is this application isn't perfect. One of the limitations is that it requires an n-bit binary approximation. And the problem with that is once you get towards something that's not smooth, you need a very small delta value, very small perturbation, and that means you need a lot of precision. Now, you need precision beyond what is really capable of the quantum simulator for some cases, and in this particular case when you're near this non-smooth region. So I did kind of a cheat where I did an adaptive precision where I started low and then it tries to figure out what it should be, and then if it needs over 8 qubits, then I just switched to an analytic solution. So it's iterating. It blew up. I tried to do it the pure way, and then it blew up. So I did a little bit of a cheat. So I run this function. The mass is 1, the initial condition, and the position, the velocity, the starting h. We're going to run a simulation for 10 seconds, sampling every 0.2 seconds, generate a trajectory. So I have this printing where we are and which estimator is used. So you can see that so this is x, as we get near 0.5, it starts to mix the classical and the quantum gradient. But if you're away from 0.5, it's pretty much always the quantum gradient. Okay, and then we output that, and we get a nice smooth trajectory where it's oscillating between 0 and 1, as we would expect. All right, and then, so that's the demo. And just for reference, these are the top paper is Jordan's original work on this. The second paper is an application of this algorithm. Very good paper. I recommend reading it. And then the code for this is on my fork of Grove on my GitHub, which is linked here. Thank you.